Alright, in this video, we're going to be solving the hardest probability and statistics 1 questions that Cambridge asked in 2025. So make sure to like the video, subscribe, and let's dive right in. Number 5. The mass of peaches sold per day in a supermarket is normally distributed with mean 65.8 kgs and standard deviation 9.6 kgs. Okay, so mass of peaches normally distributed mean 65.8 and standard deviation 9.6, so variance is 9.6 squared. Part A says find the probability that the mass of peaches sold on any given day is between 56 kgs and 75 kgs. Actually, I'm gonna change this from a P because I don't want to be writing the probability of P. Okay. So it says find the probability, this is part A, that our mass is between 56 and 75. Okay. So the first thing is to standardize. So standardize the 56. Remember your formula for standardization, x minus mu over sigma. So 56 minus our mu, which is 65.8, over sigma, which is 9.6, is less than. When you standardize the m, you get big Z, and then standardize the 75. So 75 minus 65.8 over 9.6. And let's simplify that. That's 56 minus 65.8 over 9.6. That gives us negative 1.021 to 3 decimal places. And if we do the same for the 75, we get 0.958. Okay. And you can sketch this out. We want the area between 0.958 and negative 1.021. This area here. That's what we're interested in. So, I mean, you can either memorize these formulas, right? Or you can, if you don't know the formulas, then you pretty much have to figure it out and derive it on the spot. But if you want the formulas, just go to my website. I'll link it down below in the description. It's not the first link, it will be the second link. The first link is sign up for tutoring. The second link will lead you to the page where you can just go through all the formulas you need to know when you are dealing with the normal distribution, right? So here, the formula that you get will be phi of 0.958 minus 1 minus phi of 1.021. But the idea here is that we're just saying the area to the left of 0.958, which is your phi of 0.958, minus the area to the left of negative 1.021. There's this handy trick that says phi of negative z is equal to 1 minus phi of z. So with that in mind, then that just means phi of 0.958 minus this part here becomes that 1 minus phi of 1.021. If you ever get stuck in the exam and you're trying to figure out what to do, this is how you'd approach it. But hopefully you should be comfortable with just recalling the formulas because that's much faster and will save you quite a bit of time. So go to your tables, read out phi of 0.958, you get 0.8309. I can't read my own handwriting. I'll just trust that that's 09. Minus 1 minus phi of 1.021, which is 0.8463. Okay. Let's punch that into the calculator and hope that it gives us the correct answer, which is 0.677. Perfect. That's part A. Now we are given that the mass of cherries sold per day in a supermarket is normally distributed with mean 72.4. So C, excuse me, my body is fighting me today. It wants me to not do math, but the math must be done. C follows a normal distribution with our mass is 72.4 and standard deviation is sigma, so variance is sigma squared. It is known that on 10% of the days, less than 59.1 kgs of cherries are sold. Okay. So our random variable C here is representing mass of cherries sold per day, right? Cherries sold per day. We are told that the probability that the mass of cherries sold per day, which is C, is less than 59.1 kgs is equal to 10%. I hope that makes sense. The mass of cherries sold per day, that C, is less than 59.1 on 10% of the days. Okay. So we are going to use that to help us solve for sigma. So we are going to standardize. If you standardize your C, you get Z. By the way, this should probably come before the distribution. You have to define your variable first. I just defined it so that it actually makes sense how this probability part comes about. Anyways, standardize your 59.1, subtract mu, which is 72.4, over your sigma, and this is still equal to 0.10. So probability that Z is less than 59.1 minus 72.4, that is negative 13.3 over sigma is equal to 0.10. So now for readability, I'm just going to say let Z, small z, equal negative 13.3 over sigma. So I can actually write this as the probability that big Z is less than small z is equal to 0.10. And so if we sketch a picture of what's going on here, you will see that what we are looking at here, we're saying that the area to the left of Z is 0.1. The area to the left of Z is 0.1. So Z has to be somewhere here so that the area to the left of Z is 0.1. Okay. And the reason this is important is it tells us what sign we're going to put on our Z value. From this diagram, I can tell that Z is clearly less than 0 since it's on the left of 0. So whatever Z value I get from my tables, I'm going to have to make it negative because I can tell from my diagram that Z should be negative. Okay. Another problem we have is that our tables actually don't allow us to read probabilities that are less than 0.5. So we'll just do 1 minus 0.1, which is 0.9. The reason our tables start from 0.5 is because this 0.9 and this 0.1 are bound by the same Z value, right? The cutoff point there is the same. So it wouldn't be necessary for them to put table values for 0.1, 0.2, any number less than 0.5, because I can just find the Z value by doing the 1 minus of that number. So instead of looking for 0.1, I'll go to my tables and I'm doing argphi, which just means I'm reading my tables in reverse. So Z is equal to argphi of that. But keep in mind that we've already concluded from our diagram that Z has to be negative, so it has to be negative argphi of 0.9. So argphi of 0.9 means we're going to go to our tables and we're going to read them in reverse. So z is equal to negative. If you do argphi of 0.9, you're going to get 1.282. Okay. So this means that, remember earlier we said z is equal to that. This means that negative 1.282 has to be equal to negative 13.3 over sigma. And so sigma has to be negative 13.3 divided by negative 1.282. And so sigma therefore has to be 13.3 over 1.282, which is 10.423 significant figures. And that's our final answer. Now we are told that the supermarket is open 7 days a week. 7 days a week. So this should hint to a binomial distribution because we've got 7 trials, right? Our number of trials has now been fixed. Part C says find the probability that in a randomly chosen week, the first day on which less than, okay. So now first day actually hints not to a binomial distribution, but to a geometric distribution. Find the probability that in a randomly chosen week, the first day on which less than 59.1 of cherries are sold is the 5th day of the week. Remember, a geometric distribution is just looking for that first success. And here we're looking for that first day with less than 59.1 kgs. So a success is a day that has less than 59.1 kgs. So I can define my random variable x here and say, let this be the number of days up until the first day on which less than 59.1 kgs of cherries are sold. So now this part here is just defining our success. So our success is the probability of getting a day with less than 59.1 cherries. So we can write that x follows a geometric distribution, and we were actually given this probability. If you go back to the stem of part B, where it says the mass of cherries sold per day in a supermarket is normally distributed with mean that and standard deviation that, it is known that on 10% of the days, less than 59.18.1 kgs of cherries are sold. So our probability of getting a day with less than 59.1 kgs is 0.1. That's our probability of success. And so coming back to our question here, they're saying find that the first day this happens is the 5th day. So the probability that x is equal to 5. We have our first success on the 5th day. And you go to your MF19, you get your formula for probability of a geometric distribution, and that's going to be q to the n minus 1 times p. So in this case, our q is 1 minus 0.1, which is 0.9 to the power of 5 minus 1, 4 times 0.1, 0.9 to the power of 4 times 0.1. That gives us 0.0656. And then we've got part D, which says, find the probability that in a randomly chosen week, the first day on which less than 59.1 kgs of cherries are sold before the 5th day of the week. Okay, that's a mouthful. So they want us to find the probability that x, right, x being the first day on which less than 59.1 kgs of cherries are sold, is before, so less than the 5th day of the week, less than 5. Okay. So this is going to be, by the way, even though here we were told that the supermarket is open 7 days a week, the reason we concluded that this is a geometric distribution is because we're tracking the number of trials up until a first success, which is literally the definition of a geometric distribution. So the 7, yes, it kind of hints to a binomial distribution, but remember, a binomial distribution would say that you're going to open the supermarket for 7 days, and then of those 7 days we want to count our successes, which is not what we're doing here. We're tracking up until first success. Part D, probability that x is less than 5. So here, because this is discrete, when I say less than 5, I mean x is, remember, we don't take x as 0 because you actually have to carry out at least one trial to get a success. So we start from x is 1, 2, 3, and 4 is the last number that we take, right? Less than 5, because this is discrete. So this is essentially the same as x is less than or equal to 4. The reason why I wrote it like that is because I want to use this beautiful formula that says the probability that x is less than or equal to r is equal to 1 minus q to the r. If it was greater than, the formula you would have used is this. So these are two formulas you can use to save you the work. So if it's less than, you try to force it here. If it's greater or equal to, you force it here, and then you use the formula. So in our case, that's 1 minus q is 0.9 and r is 4. So probability that x is less than or equal to 4 is equal to 1 minus 0.9 to the 4, which is 0.34423 significant figures. Question number 4. Every Saturday, a particular community holds a puzzle event to raise money for a new leisure center. Competitors attempt to solve a puzzle as quickly as possible. Last Saturday, 600 competitors took part. The times taken to complete the puzzle were normally distributed with mean 32.4 minutes and standard deviation 2.5 minutes. Okay. Part A says how many competitors would you expect to have times within 1.2 minutes of the mean time? Okay, before we get there, let's digest what's going on. Going to define a random variable t. Let t be the random variable that's tracking time taken to complete the puzzle. And we know that this time follows a normal distribution with mean 32.4 and standard deviation 2.5, so variance is 2.5 squared. And part A requires us to find how many competitors we would expect to have times within 1.2 minutes of the mean time. So what we can do is to find what is the probability of just one competitor having a time within 1.2 minutes of the mean time. And once we know what the probability is for one person, we can multiply that by 600, because that will give us the expectation of how many of 600 would expect to have times within 1.2 minutes of the mean time. So if they say 1.2 minutes of the mean time, right? I think it probably makes more sense if we represent this visually. My bell curves today are on point. Don't know what's happened, but they're curving. Anyways, our mean here is 32.4, and we're saying 1.2 of the mean time. So that can mean either 32.4 plus 1.2, right? Which would be maybe, let's say, somewhere here. This would be 32.4 plus 1.2, so 36.3 33.6, or the other way, which is 32.4 minus the 1.2. Minus 1.2, which is 31.2. Because any time within the space here is within 1.2 off of the mean, right? So we need to find the probability of a time being within this interval. So that means what we're actually interested in is the probability that t is between 31.2 and 33.6. Okay, and so we go ahead and we standardize. So that's 31.2 minus the 32.4 divided by sigma, which is 2.5, is less than t becomes big Z, which is less than 33.6 minus the mean, which is 32.4, over our standard deviation 2.5. And so that's the probability of, let's punch that into the calculator, 31.2 minus 32.4 over 2.5, which is negative 0.48, is less than Z. Do the same for 33.6 and we get positive 0.48. Okay. And so if we draw a bell curve here, this is now in terms of Z. The initial one was for our times. Okay. Now this bell curve doesn't want to do bell curve things. So now that we've standardized, our mean is 0. And we've got Z being negative 0.48 and Z being positive 0.48. And so that means the area we want here is that area in there. And to get that area, it's going to be, or we can use this formula, 2 phi of 0.48 minus 1, which simply comes from saying the area to the left of 0.48 minus the area to the left of negative 0.48. If you simplify that, manipulate that, you get to 2 phi of 0.48 minus 1. Right, so that's 2 times phi of 0.48. Read from your tables, you should get 0.6844 minus 1. And, oh, this is not the final answer. This is 2 times 0.6844 minus 1, which is 0.3688. So this is the probability of one competitor having a time within 1.2 minutes of the mean time. What about 600 competitors? So that becomes 600 multiplied by 0.3688. And so that gives us 221.28. So round up, that means we would expect 222 competitors to have a time within 1.2 minutes of the mean time. So 222 competitors. That is part A. Now we're told that in this Saturday event, 60% of competitors had times less than 36.0 minutes. Okay. Part B says 9 competitors who took part in this Saturday's event are selected at random. So we're taking 9 competitors. And the question says find the probability that at least 2 and fewer than 8 of these competitors had times less than 36.0 minutes. So hopefully you can see that this is now a binomial distribution question. This is probability of success. This is your fixed number of trials. Okay, so let's actually define our random variable. Let x be RV, number of competitors who took part in Saturday's event. And what is the success? They had a time less than 36 minutes and had times less than 36.0 minutes. You don't have to write this down, but I'm writing it so that you can actually understand what's going on. So here x follows a binomial distribution and our number of trials is 9 and our probability of success is 60% or 0.6 because we are counting the number of competitors who had a time that was less than 36.0. That's our success. So it's either you've got less than 36.0 or you don't. So the question wants the probability that we have at least, so greater or equal to 2 and fewer than 8. So at least 2 and fewer than 8. In fact, I'm going to rewrite this as, if we say at least 2 and fewer than 8, we're looking at x is 2, 3, 4, 5, 6, and 7. This means I can actually just write this as being the probability that x is less than or equal to 7. So note that less than or equal to 7 will also include 0 and 1. So it will be 0, 1, 2, 3, 4, 5, 6, and 7. So I have to subtract x's less than or equal to 1 because I don't actually want to include that. So we can then do minus the probability that x is less than or equal to 1. All right. And then we can evaluate x is less than or equal to 7 and x is less than or equal to 1 and then subtract the 2. The alternative would be to evaluate x is 2 plus x is 3 plus x is 4 plus x is 5 plus x is 6 plus x is 7, which I'm sure you understand is very long. So if we want to do probability that x is less than or equal to 7, I know that I can rewrite that as 1 minus the probability that x is greater than 7. And given that we're going to 9, that's not too challenging. And then probability that x is less than or equal to 1, that's just the probability that x is equal to 0 or x is 1. So that's not long either. So in the first bracket here, I'm looking at 1 minus the probability that x has to be greater than 7. So x has to be either 8 or 9. All right. And so now we can go ahead and evaluate our probabilities. So I've got 1 minus, we want to do 8 and 9. So 9 choose 8 times 0.6, which is our probability of success, to the 8 times, if success is 0.6, then failure has to be 0.4 raised to the power 1. And then the last one, 9 choose 9. 9 choose 9 is 1 times 0.6 raised to the power 9 times 0.4 to the 0. 0.4 to the 0 is 1. So that's just 0.6 to the 9 minus, then we want to do x is 0. For x is 0, it's just going to be, we want no successes, so we have to fail 9 times, which is 0.4 to the 9, plus x is 1, which is 9 choose 1 times 0.6 to the 1 times 0.4 to the 8. And so we can punch this into the calculator. That is 1 minus 9 choose 8 times 0.6 to the 8 times 0.4 plus 0.6 to the 9, and we close our bracket, minus, open another bracket, 0.4 to the 9 plus 9 choose 1 times 0.6 times 0.4 to the 8, close bracket. That is 0.926. And that there is our final answer. Now in part C, we are given that 80 competitors who took part in this Saturday's event are selected at random, right? Use a suitable approximation to find the probability that more than 50 of these competitors had times less than 36.0 minutes. So we're still interested in a success being time less than 36.0. Okay. So they've asked for a suitable approximation. At the AS level, the only approximation you will do is the normal approximation to the binomial distribution. So immediately you should know that if I define my random variable, what do we want to call it? I don't like is. Let's call it E. Let E be the random variable, the number of competitors with time less than 36.0 and 36.0 minutes at our event. Out of 80 competitors, you can include that if you want to be, very by the book. We're going to say E follows a binomial distribution with N being 80 and probability of success from earlier. We were told that 60% of the competitors had times less than 36.0 minutes. So that's 0.6. Okay. So this becomes the probability that, in fact, before we even get to probability, we want to use an approximation, right? I know the question doesn't ask you to justify the use of the approximation, but generally you want to check that NP is greater than 5 and NQ is greater than 5 for you to be able to use a normal approximation to the binomial distribution. So it's always a good thing to just double check that these conditions are met, even though at AS level, if they ask for an approximation, this is the approximation that you will use. So NP, this becomes 80 times our P, which is 0.6. 80 times 0.6, that's 48, which is clearly greater than 5. And NQ is 80 times 0.4, which is 32, and this is also greater than 5. So since these conditions are met, this allows us to use a normal approximation to the binomial distribution. And so here we can say that we're using E. E follows now a normal distribution, and our mean is going to be NP, and our variance is going to be NPQ. So mean is the mean of a binomial distribution. Variance is the variance of a binomial distribution. NP we already calculated to be 48. NPQ, we need to find what that is. So that's 80 times 0.6 times 0.4. And that gives us 80 times 0.6 times 0.4. That gives us 19.2. So we have that E follows a normal distribution with our mean 48 and our variance 19.2. All right. Now let's actually go back to the question and see what we're trying to solve. So we want the probability that E, so more than 50 of these competitors have times less than 36.0. So more than 50. Okay. But remember, this question was defined under a binomial distribution, which is a discrete distribution. But now we've approximated a normal distribution, which is a continuous distribution. So we need to take that into account. And we do that by applying what we call continuity correction. This number 50 under discrete conditions represented exactly 50. But now, under continuous conditions, this 50 represents any number from 49.5 all the way up to 50.5. So if I'm saying I want e to be greater than 50, it means I want e to be greater than any number within this interval, because any number within this interval represents 50. So that means I want e to be greater than 50.5, because that ensures that I don't include any number within this interval. So probability that e is greater than 50.5. And now we can standardize. So this becomes z is greater than 50.5 minus the 48 over our standard deviation, which is square root of our variance. And so that's probability that z is greater than, punch that into the calculator, that is 50.5 minus 48 over the square root of 19.2. And we get 0.571. And this we can write as 1 minus phi of 0.571. So that is 1 minus read of phi of 5.71 from the normal distribution tables. That's 0.7160. And so if we subtract this, we should get 0.284. And that is the final answer. Question number 6. Part A. Find the number of different ways in which the 10 letters in the word amalgamate. What a word. Amalgamate can be arranged so that there is an M at the beginning, an M at the end, and no A's together. Okay, those are a lot of restrictions. Okay, so our restrictions are, we want the M's at the end, right? An M at the beginning and the other one at the end, and then no A's together. Okay. So one way we could do this is to approach the question as you'd normally approach a question in which you're finding like no letters together, where you're going to do the total minus the together version, right? But here, if we're going to go that approach, then what does together actually mean? If we read the question, they're saying no A's together, so I can't have A, and maybe even like TG, let's say we've got L here. I can't have even two A's next to each other. I can't have three A's next to each other. I can't have all four A's next to each other. So if we go the minus together option, I would have to calculate all four A's together, three of the A's together, and two of the A's together. That's what would count as A's together, and we'd have to subtract that from our total. So we could go that approach, but there is an easier way to do this. The total minus together approach makes sense if the letters that are not supposed to be together, if there are only two of them, then that's pretty much the easiest way to go about it. But in this instance, what we want to do instead is we are saying that we want the M's at either end, right? That's the first restriction. And then the letters that are not A's, if we take out the M's and we take out the A's, I'm left with 1, 2, 3, 4 letters. So 1, 2, 3, 4 letters. Right, I'll put this down. We've got LG and TE. If I want to ensure that I don't have any A's being next to each other, then I can put an A here, or I can put an A here, or I can put an A here, and an A here, and an A here. So this ensures that there's always at least one letter between the two A's. And that's exactly what we're looking for, right? Because we don't want any A's to be together. So that's the approach. And bear in mind that we can't have an A there because the M's have to be at either end. So now how would we find the number of arrangements for this? So just shuffle the blue letters first. How many different arrangements are there for the blue letters? That's just 4 factorial. The red letters are fixed, the M's, so you don't need to do anything with those. And with regards to the green letters or the green spaces, these are the spaces that the A's can take up. We've got 4 A's that we want to arrange in these 5 spaces, but we don't actually care the order in which the A's are. If I put an A here and an A there, if I swap these two, I'm not going to be able to tell the difference because they're all identical, right? So that's why I have to use a combination. If the A's were different, right? If this was like A1 and A2, if I swap them, then I would notice a difference. So in that case, I would have had to use a permutation. But since these are identical, I can just use a combination and say that I'm trying to arrange 4 A's into 5 spaces. Since they're identical, it becomes a combination. So 5 choose 4. And so that's 4 factorial times 5 choose 4. Where is my calculator? What does that give us? That is 5 times 4 factorial, which is 120. And that is the final answer. Part B. Find the number of different ways in which the 10 letters in the word amalgamate can be arranged with exactly 3 letters between the two M's. So we've got the word amalgamate. Forget the restrictions from part A. We now have completely new restrictions. We are told that there will be exactly 3 letters between the two M's. So let's put an M here and let's put an M here. And then I'm going to put 1, 2, 3 letters. That's 5. So I should have another 5. 1, 2, 3, 4, 5. Okay, so that could be A, L, A, G, A, T, E. I feel like I'm missing a letter. Amalgate. I spelled amalgate. Okay, amalgamate. All right. So there should be an extra A there. All right, so this is the situation that we're looking at, right? So the way we want to approach this, obviously the two M's can move. For example, I could have something of the form M, M, and then 3 letters in between here, and then 1, 2, 3 letters on that side. The M's can move along the line, right? But we'll consider that at the end. For now, let's just focus on the blue letters. And how many different ways can we arrange the blue letters? So that's 1, 2, 3, 4, 5, 6, 7, 8. So 8 factorial. Do we have any repetitions? Yes, the A's appear 4 times, so over 4 factorial. Now we have to think about the M's. They did not fix the position of the M's. The only restriction is that they have to be exactly 3 letters between the two M's. So that means, like we mentioned, I could have space and then M, then rather let me put an M here. Then I could have 1, 2, 3, 1, 2, 3, or I could have 2 spaces, 1, 2, 3, 1, 2, and then I could have my M's here, right? The point is the M's can move along the line as long as they're maintaining 3 letters between. So we need to count how many positions in which we can have the M's and then multiply that by 8 factorial over 4 factorial. So in this case, you can count that by just monitoring how many places this last M can take up. So it can take up this position or that position or that position or that position or that position. Now it's reached the end of the line. So we have to multiply by 6. And so that there gives us 8 factorial over 4 factorial by 6, which is 10,080. And that is the final answer. Now we are given that 5 letters are selected from the word amalgamate. I need to spell it right this time, amalgamate. Find the number of different selections in which the 5 letters include at least one M and at least 2 A's. Okay. So let's write down all the possible scenarios that satisfy this restriction of at least one M and at least 2 A's. So for starters, the most obvious one, MAA. And that means we'd have 2 free slots since we're selecting 5. And then I could also have 2 M's, 2 A's, and then 1. Or I could also have 1 M and 3 A's, right? There's at least 1 M, at least 2 A's. Or I could also have 1 M and 4 A's. Or I could have 2 M's and 3 A's. 1, 2, 3, 4, 5. That looks like everything. 1, 2, 2, 2, 1, 3, 1, 4, 2, 3. Okay. And then you just evaluate the number of different possible selections for each scenario. So for this first scenario, what we're doing is we've already selected the M's and the A's that we want. So in our selection pool, we're only going to have LG and the TE. Those are the 4 letters we're selecting from because we don't want to, by mistake, pick another A or another M. We've already accounted for the A's and the M's that we want to select. So we're picking from these 4 now in these empty slots. So for those 2 slots, I want to pick from 4. So 4 choose 2. And then here, from those 4, I want 1. So 4 choose 1. From those 4, I want 1. So 4 choose 1. From those 4, I want 0 because all my slots are occupied here. From those 4, I want 0. And so if we evaluate this, 4 choose 2 is 6. 4 choose 1 is 4. 4 choose 1 is 4. 4 choose 0 is 1. 4 choose 0 is 1. Okay. Let's tally that up. So total is 6 plus 4 plus 4 plus 1 plus 1. And so therefore, the total has to be 16. Question number 6. A company sells bags of pasta. The masses of large bags of pasta are normally distributed with mean 2.50 kgs and standard deviation 0.12. Part A. Find the probability that the mass of pasta in a randomly chosen large bag is less than 2.65 kgs. Okay, so the masses of large bags of pasta follow a normal distribution with mean 2.50, standard deviation 0.12, so variance is 0.12 squared. Okay, and then the part A, they want the probability that the mass of pasta is less than 2.65. Okay, so this is a very straightforward question. You just standardize. Probability that Z is less than 2.65 minus the mean, which is 2.50, over the standard deviation. So Z is less than 2.65 minus 2.50 over 0.12, and you get 1.25. We want to read off phi of 1.25 from our tables, and that would give us the final answer. You go to your tables, you're going to get 0.8944. So the 3 significant figures, 0.894. Now we're given that a restaurant manager buys 160 large bags of pasta. So the manager buys 160 large bags of pasta. So the large bags from part A, they buy 160 of these. Find the number of bags for which you would expect the mass of pasta to be more than 1.65 standard deviations above the mean. Okay, so questions like these, the way you want to approach them is to just first start by looking at one bag. What's the probability that one bag has a mass of pasta more than 1.65 standard deviations above the mean? Once I know that for one bag, I can then figure out of 160 bags, how many would I expect to have, in this case, mass of pasta more than 1.65 standard deviations above the mean. And you just do that by multiplying the probability you'd have gotten for one by whatever your number is, in this case, 160. So what we're going to do here is we want the probability that L is mass of pasta is more than 1.65 standard deviations above the mean. I hope that makes sense. I'm going to sketch it out. I imagine the diagram would be a lot more clear. So for our distribution, we had that L follows a normal distribution with mean 2.50, 2.50, and 0.12 squared. So my mean here is going to be 2.50. So we want more than 1.65 standard deviations above the mean. So what is a standard deviation? Here a standard deviation is 0.12. So what is 1.65 standard deviations? 1.65 sigma is 0.12 times 1.65, which is 0.12 times 1.65. That is 0.198. So if I want more than 1.65 standard deviations, I want more than 0.198. But they're saying more than 0.198 above the mean. So that becomes 2.5 plus the 0.198, which is 2.698. So it would be maybe somewhere here, 2.698. And we're interested in the area to the right. So we can write this as the probability that L is greater than that 2.698 figure. And then we can go ahead and standardize this. So Z is greater than 2.698 minus our mean. Our mean is 2.50 divided by sigma. Sigma is 0.12. If we punch this into the calculator, this is 2.698 minus 2.5 over 0.12, which is 1.65. I can write this as 1 minus phi of 1.65. Got my tables, read off phi of 1.65. I'm going to get 0.9505. And this gives me, this is 1 minus 0.9505. That's 0.0495. So this is the probability that one large bag has a mass of pasta more than 1.65 standard deviations above the mean. So this is for one bag. What about 160 bags? We just multiply. So 0.0495 times the 160. What does that give us? 7.92. And we can't have 0.92 of a bag of pasta. We're just going to buy the whole bag, right? So we'd have 8. You round up. So therefore, I'd expect 8 bags to have a mass of pasta more than 1.65 standard deviations above the mean. Now we are given that the masses of small bags of pasta I'll call that S, are normally distributed with mean mu and standard deviation sigma. Tests show that 77% of these bags have masses greater than 1.26 kgs and 44% have masses less than 1.35 kg. Part C, find in either order the value of mu and the value of sigma. Okay, so part C, we are told that tests show that the probability that the masses of the small bags of pastas are greater than 1.26 is 0.77, because 77% of the bags of pastas have mass greater than 1.26 kgs. And on the other side, we have that the probability that the masses of the small bags are less than 1.35 is equal to 44%, so 0.44. And so here, what we want to do is we want to standardize this. So if I standardize S, I get Z, and that's 1.26 minus our mean over our sigma. This is still equal to 0.77. And you do the same here, so that Z is less than 1.35 minus mu over sigma is equal to 0.44. The idea would be to eventually simplify these two equations until we end up with two equations in terms of mu and sigma, and we can solve those two equations simultaneously. So for now, I'm going to work on this first equation here. And I want to say let Z1 equal 1.26 minus mu over sigma, so that this is easier to read. So I have the probability that Z is greater than Z1 is equal to 0.77. If we draw the bell curve for this, what we are saying is that the area to the right of Z1 is 0.77. So if I have 0 here, the area to the right of Z1 has to be 77%. So that means Z1 has to be somewhere here for that to be possible. So that the area here is 77%. 0.77. And I hope you can see that from this diagram, Z1 therefore has to be negative, right? Because it's to the left of 0. So Z1 is going to be negative, and we want to read our tables in reverse to find a Z value that corresponds to a probability of 0.77. So Z1 is going to be negative, go to your tables, read off arc-phi of 0.77, and that's going to be equal to 0.739. Okay. Can't read my own handwriting. Shocking. All right. So if we go back up, we have that Z1 is equal to that. So that must mean negative 0.739 is equal to 1.26 minus mu over sigma. And so if we multiply both sides by sigma, I have negative 0.739 sigma is equal to 1.26 minus mu. And so mu has to be 0.739 sigma plus 1.26. All right. And we want to do the exact same thing for this other equation. So we are going to say let Z2 equal 1.35 minus mu over sigma, so this part here. And so that becomes the probability that Z is less than Z2 is equal to 0.44. And we also want to sketch a bell curve for this. And that is going to be 0. And here what we are saying is that the area to the left of Z2 is 0.44. So the area to the left of Z2 is 0.44. So that must mean that Z2 has to be somewhere here so that the area to its left is 0.44. There's no way I can put Z2 on this side and claim that the area to the left of Z2 is 0.44. It wouldn't make sense. Okay, so 0.44. So that means the unshaded region here has to be 1 minus that, which is 0.56. Okay. So from our diagram, again, I hope you can tell that Z2 therefore has to be negative because it's to the left of 0. So we want to do negative arc phi of 0.56. And so go to your tables, read off negative, or just go read off arc phi of 0.56 because it's always going to be positive. And if you read off arc phi of 0.56, you should get 0.151. Okay. And remember, we say that Z2 is equal to that. So I can say that negative 0.151 has to be equal to 1.35 minus mu over sigma. Okay. And now we can multiply both sides by sigma. So I've got negative 0.151 sigma is 1.35 minus mu. And let's make mu subject of the formula. So mu is 0.151 sigma plus 1.35. And so now we end up with these two equations in terms of mu and sigma, and we can solve our two equations simultaneously. We've already made mu subject of the formula in both of them, so we can just equate the two. So I have 0.739 sigma plus 1.26 is equal to 0.151 sigma plus 1.35. And I'm going to move this to the left and that to the right. So this becomes 0.739 sigma minus 0.151 sigma is equal to 1.35 minus 1.26. Okay. So on the left, I've got 0.739 minus 0.151, and so 0.588 sigma. And on the right, I have 0.09, and so sigma has to be 0.09 divided by 0.588. So sigma is 0.09 over 0.588. That gives us 15 over 98. To three significant figures, that's 0.153. And we can use this to find mu. So mu is going to be 0.739 times sigma. I'll use the exact value, so I'll use the 15 over 98 plus the 1.26. So mu is equal to 0.739 times 15 over 98 plus 1.26. And that gives us 1.37, correct to three significant figures. So we can conclude that therefore mu is 1.37 and sigma is 0.153. And that will be the final answer. Question number 4. Bag A contains 8 red marbles and 3 blue marbles. Bag B contains 4 red marbles and 1 blue marble. Okay. Just gonna note it down. So bag A contains 8 red and 3 blue. Bag B contains 4 red and 1 blue. Okay. One marble is chosen at random from bag A. If the marble is red, it is discarded. If the marble is blue, it is placed in bag B. So I know if I pick red from here, I discard. But if I pick blue, it goes into bag B. Okay. A marble is then chosen at random from bag A. If the marble chosen is red, so if we pick red from here, we discard. And then if the marble chosen is blue, it's put in bag A. So if we pick blue, okay. And then a marble is now chosen at random from bag A. Complete the tree diagram below by entering all the remaining outcomes and probabilities. Right, so they did the first one for us, 8 over 11 and 3 over 11. If we pick a red marble from bag A, we're going to discard it. So it means when I pick from bag B, I've got 4 red marbles and 1 blue marble. So I'm picking from 5. And from those 5, here, they didn't label this. I thought they labeled that. I'll read. Let's just first fill in red, blue, and then red, blue, red, blue, red, blue, red, blue. That 5 looks like a 6. We said if we pick a red marble from bag A, we discard it. So that means when we look at bag B now, we only have 4 red marbles and 1 blue marble. So I'm picking from 5. And if I want red, that's going to be 4 out of 5. And again, for blue, I'll be picking out of 5. And there's a 1 in 5 chance. Then here, just to double check that this is correct, they're saying there's a 3 out of 11 chance of picking a blue marble from bag A initially, yeah? If we pick a blue from bag A, our new bag B looks like this. We now have 4 red marbles and 2 blue marbles, meaning that when we now pick from bag B, there's a 4 out of 6 chance of getting a red and a 2 out of 6 chance of getting a blue. So that's fine. And now let's do this last set of branches. So now let's assume from bag B, we pick a red. What happens to the red? The red is discarded. So I'm just looking at. Okay, so let's just recap what's happened down this first branch. So I picked a red from bag A, meaning in bag A, I currently have 7 red and 3 blues because we picked a red, right? And then in bag B, we picked a red and we discarded it. We don't care about that. Then we proceeded to pick from bag A. So that means in bag A, I'm looking at 7 reds and 3 blues. So I've got a 7 in 10 chance of picking a red and a 3 in 10 chance of picking a blue. Okay. So now, assuming we picked a red from bag A, we're looking at 7 reds and 3 blues, right? Then from bag B, we picked a blue. So that blue is then put into bag A. So now what we actually have is 7 reds and 4 blues in bag A. So now I'm saying that I've got, out of 11, I have a 7 in 11 chance of picking a red and then a 4 in 11 chance of picking a blue. Okay, now let's look at the last 2 branches. So assuming we picked a blue first from bag A, here I'm just focusing on bag A because that's what we need to fill in at the end. Assuming we picked a blue from bag A, it means I have 8 red marbles, but because I picked a blue, I must only have 2 blues in bag A, right? And then here, let's say we pick a red from bag B, we know that's just discarded. So my bag A still looks like this when I come again and pick from that bag. So I'm picking from 10 and I've got an 8 in 10 chance of getting red and then a 2 in 10 chance of picking blue. Now let's say I picked blue in bag A at the beginning, so I'm looking at 8 reds and 2 blues in bag A. Then from bag B, I picked blue, so we know that blue is added to bag A. So I actually have 3 blues in my bag A. Alright, so that means I'm picking from 11 and I have an 8 in 11 chance of getting a red and a 3 in 11 chance of getting a blue. And that's going to be our complete tree diagram. Then part B says find the probability that all 3 marbles chosen are the same color. So that's either red, red, red or blue, blue, blue. So that's red, 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 or blue, blue, blue. So probability of red, 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 that's going to be 8 over 11 for red and A, and then 4 over 5, and then 7 and 10. So times 4 over 5 times 7 and 10 plus blue, 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 that's 3 over 11 times 2 over 6 times the 3 over 11. So 3 over 11 times 2 over 6 times 3 over 11. Let's punch this into the calculator. That's 8 over 11 times 4 over 5 times 7 over 10 plus 3 over 11 times 2 over 6 times 3 over 11, and this gives us 0.432. And that is the final answer. Question number 2. Kayla has a bag containing 3 red marbles, 1 blue marble, and 2 green marbles. Okay, so Kayla's got a bag with 3 red, 1 blue, and 2 green. She selects 1 marble from the bag at random and does not replace it in the bag. She repeats this process until she obtains a green marble. The random variable x is the number of marbles that she needs to select until she obtains a green marble. Part A. Draw up the probability distribution table for x. So in fact, I'm just going to change our bag here to show that we've got 2 greens and 4 that are not green. So 4 not green, because really we don't care what color they are if they're not green. So we need to draw a probability distribution table. So we're going to have x and then probability that x is x. So x is the number of marbles that she needs to select until she obtains a green marble. So for her to obtain a green marble, she has to at least select 1 marble. So the smallest value of x we can have is 1. And to get that 1, that's going to be a 2 out of 6 chance. And then she could also get a green in 2 trials, meaning that she first selects not green, then she selects a green marble. So that's the probability of not green and then green marble. So that's going to be not green, we have a 4 in 6 chance since we're starting with a bag of 6. But once we select 1 marble, we've got 5 marbles remaining because we're told that she does not replace the marble. Okay. And from there, we're saying we want to pick a green, so that's going to be 2 out of 5. So this is 4 over 6 times 2 over 5, which is 4 over 15. 4 over 15. She can also take 3 marbles. She can also select 3 marbles until she obtains green. So that's going to be not green on the first pick, and then not green on the second pick, and then green on the third pick. So that's going to be 4 out of 6 for not green on the first pick. Once we pick 1 marble, we have 5. Since we selected a not green on our first pick, we only have 3 not greens remaining. And then on the third pick, we've got 4 remaining because we've already selected 2 marbles and only 2 of those are green. So that's going to be 4 over 6 times 3 over 5 times 2 over 4, which gives us 1 over 5. And then we can also have, and then she can also select 4 marbles until the first green. So that's going to be not green, then not green, then not green, and then finally green on the 4th marble. So not green on the first attempt is 4 out of 6. We're now left with 5 marbles and only 3 of those are not green. Then now we're left with 4 and only 2 of those are not green. And now we want to pick a green, but we're left with 3 and only 2 are green. So that's going to be 4 over 6 times 3 over 5 times 2 over 4 times 2 over 3, which is 2 over 15. And since we've got 4 not green marbles, the worst case scenario is that
we first pick all 4 not green marbles, and then on our 5th pick we get our first green marble. So the worst case scenario is having to pick 5 marbles. So that's going to be probability of not green and not green and not green and not green. Then finally we get our green. So that is 4 over 6, and then we're left with 5. Only 3 of those are not green. We're left with 4. Only 2 of those are not green. We're left with 3, and only 1 of those is not green. And in the bag we now only have 2 marbles, and both of those marbles are going to be green. So 2 out of 2. So that's 4 over 6 times 3 over 5 times 2 over 4 times 1 over 3 times 2 over 2, which gives us 1 out of 15. And this is going to be our probability distribution table. I don't have a ruler, but make sure you draw nice straight lines and draw a beautiful table. And that's our probability distribution table. A sense check is always to check if all your probabilities added up will give you 1. So we can do that just to make sure. So 2 over 6 plus 4 over 15 plus 1 over 5 plus 2 over 15 plus 1 over 15. That does indeed give us 1. So our table must at least be, so our table should be fine, should be correct. That's part A. And then part B is find the variance of x. So to be able to do that, I need our probability distribution table. So if you go to the MF19 under discrete random variables, you find the formula for variance of x, and it should say the summation of x squared p minus your expectation of x squared. So the first thing we need to find is our expectation of x, our mean. So expectation of x, the formula for that is summation of xp. It's in the MF19. So our expectation is going to be 1 times the 2 over 6 plus 2 times the 4 over 15, and we continue like this. So 3 times the 1 over 5 plus 4 times the 2 over 15 plus 5 times the 1 over 15. And so therefore, well, really we're not done, so I'll just remove that. So our expectation of x is, let's punch that into the calculator. So I've got 1 times 2 over 6 plus 2 times 4 over 15 plus 3 times 1 over 5 plus 4 times 2 over 15 plus 5 times 1 over 15, and that is 7 over 3. Okay. Now we need to find variance. We found the expectation of x. We also need the summation of x squared p before we can get our variance. So the summation of x squared p is just squaring your x values here. So it's the same as your mean, except all your x values are squared now. So 1 squared times 2 over 6 plus 2 squared times 4 over 15 plus 3 squared times 1 over 5 plus 4 squared times 2 over 15 plus 5 squared times 1 over 15. And so the summation of x squared p is equal to, let's punch this into the calculator, that's 1 squared times 2 over 6 plus 2 squared times 4 over 15 plus 3 squared times 1 over 5 plus 4 squared times 2 over 15 plus 5 squared times 1 over 15, and that gives us 7. And so now we just substitute into our variance formula. So the var of x is equal to 7 minus our expectation squared. And so therefore, if I punch that into the calculator, that is 7 minus the 7 over 3, and this is squared. So that gives us 14 over 9, and that is the final answer. By the way, if you like the way that I break down questions and you're struggling with your AS or A level maths, or you really just want to make sure that you get the dream grades, the exact grades that you need to get into your dream university, then click the first link in the description down below to book a free discovery call with me, and I'll help you achieve those dream grades. Question number 5. Chen has 3 boxes. Box A contains 5 counters, of which 3 are white and 2 are yellow. Okay, just gonna note that down as we go. So we've got box A has 5 counters, 3 are white and 2 are yellow. So this is A. And then box W contains 4 red marbles and 3 blue marbles. And then box Y contains 5 red marbles and 3 blue marbles. Okay. Chen chooses one counter at random from box A. If the counter is white, he chooses 2 marbles from box W at random and without replacement. If the counter is yellow, he chooses 2 marbles from box Y at random and without replacement. Draw a fully labeled tree diagram to illustrate this information, including all the probabilities. Okay. So we're going to start with box A, right? Because we know at the beginning, Chen chooses one count at random from box A. So that's where we're starting with. Box A, we're either going to pick a white counter or a yellow counter. The probability of picking a white is 3 out of the 5 marbles. A yellow is 2 out of the 5. Then if we pick white, we know he chooses 2 marbles from box W, and W contains either red or blue. So I know my first marble is either going to be red or blue. Then the second marble that I pick is also either going to be red or blue, since those are the only type of marbles we have in box W. So red or blue. And then we're told that we'll come back to filling in the probabilities. Then we're told that if the counter is yellow, he chooses 2 marbles from box Y at random and without replacement. So in box Y, again, we also have red and blue. So the first marble from box Y is either red or blue, and the second marble from box Y is either red or blue. Okay, now let's see. So if Chen picks a white marble, Chen is going to pick 2 marbles from box W. So the first marble, to get red, we're going to have a 4 out of 7 chance, which means to get blue, we're going to have a 3 out of 7 chance. They mentioned that Chen is picking without replacement. So once we pick this first marble, we actually only have 6 marbles left on our second pick. So now, assuming we picked red on our first pick, I only have 3 reds left. So I've got a 3 out of 6 chance of getting another red. And that means for blue, I only have a 3 out of 6 chance as well, since we'll still have all 3 blues in there, but we're picking from 6. Okay. Now, assuming our first pick here was a blue marble, I'm only gonna have, again, 6 marbles left, but I still have all my red marbles, so that's 4 out of 6. But now I only have 2 blue marbles left to pick from. Okay. Now if Chen picks a yellow marble from box A, we're going to box Y, and then we're going to pick 2 marbles. So on our first pick, we've got a 5 out of 8 chance of getting a red and a 3 out of 8 chance of getting a blue. Assuming our first pick is red, on our second pick we only have 7 marbles to pick from, and we know that since we picked red on our first pick, only 4 of them are red, meaning we should have 3 out of 7 for blue. Now assuming we picked blue first, we now again only have 7 marbles to pick from, but we still have all 5 red marbles, so 5 out of 7, and we only have 2 blue marbles remaining since we had already picked one. And this is our fully labeled tree diagram. Now part B says find the probability that 1 red marble and 1 blue marble are obtained. So we want the probability of 1 red and 1 blue. 1 red and 1 blue. So let's find all the different pathways that can lead us to that. So I could do white, red, blue, or I could do white, blue, red, or I could do yellow, red, blue, or I could do yellow, blue, red. Okay. So it's either white, red, blue, or it is white, blue, red, or it is yellow, red, blue, or it is yellow, blue, red. Yeah. And let's evaluate each pathway. I'm just going to copy this. So we want our first pathway is going to be white, red, blue. So white, red, and then blue. So that's going to be 3 over 5 times 4 over 7 times 3 over 6. And then we want white, blue, red. So 3 over 5, 3 over 7, and 4 over 6. So 3 over 5 times 3 over 7 times 4 over 6. And then we want yellow, red, blue. So 2 over 5, 5 over 8, and 3 over 7. So 2 over 5, 5 over 8, and that is yellow, red, blue, yellow, red, blue, 3 over 7. And then finally we want yellow, blue, red. So 2 over 5, 3 over 8, and 5 over 7. So 2 over 5, 3 over 8, and then 5 over 7. Okay, and so let's punch this all into the calculator, and that will give us the probability of 1 red and 1 blue. So this is 3 over 5 times 4 over 7 times 3 over 6 plus 3 over 5 times 3 over 7 times 4 over 6 plus 2 over 5 times 5 over 8 times 3 over 7 plus that is 2 over 5 times 3 over 8 times 5 over 7. And that gives us 39 over 70. And this is the probability of obtaining 1 red marble and 1 blue marble. Now part C says find the probability that a white counter is chosen from box A given that 1 red marble and 1 blue marble are obtained. So we want the probability of a white counter from box A given 1 red and 1 blue. So this becomes the probability of white and 1 red and 1 blue divided by the probability of 1 red and 1 blue. So I hope you can see that our top is just probability of white, red, and blue, or white, blue, and red, because they didn't really specify that it has to be 1 red marble first and then blue marble, as long as you pick 1 blue and 1 red. Okay, and then that's going to be divided by the probability of 1 red and 1 blue, which we evaluated in part B. So our numerator, we also did this working in part B. So this is our numerator, which is these two first brackets. And we know these are being divided by the probability of 1 red and 1 blue, which is 39 over 70. 39 over 70. So we can punch that into the calculator, and that should give us the probability of white given 1 red and 1 blue. By the way, the formula we used here is not provided in the MF19, and it says the probability of B given A is equal to the probability of A intersect B divided by the probability of A. So you have to memorize this formula for conditional probability. Okay, now let's punch this into the calculator. So I've got my 3 over 5 times 4 over 7 times 3 over 6 plus 3 over 5 times 3 over 7 times 4 over 6, and that's divided by 39 over 70. And that gives us 8 over 13. And that's going to be our final answer.